Hi. Today we're going to talk about the periodic table, which in a way seems a little bit late for this time of year, but no better time than the present. Speaking of time, the periodic table as we know it today, we owe that structure to a lot of scientists. But frequently, the one scientist that's singled out with really doing a lot of work is Dmitry Mendeleev. He did his work in the mid 1800s. And his work mostly centered around organizing the 60 or so elements that were known about at the time. Of course, today there are 118 that we know about. But specifically, Mendeleev is singled out because he organized his table, as many did, in terms of chemical reactivity. You can see these are the chemical formulas with oxygen and hydrogen that get made with various elements. So we knew that at the time. But most importantly were these. Mendeleev and certain others, but Mendeleev was really the one who gets known for this, spearheaded the idea that once you organized all of the elements that we knew about into a table, and when you organize them based on the compounds that they make, certain arrangements don't make sense. I mean to say, he put calcium here, and titanium we knew was the next heaviest. So these were organized by mass. But it turns out that titanium matched more with silicon, and calcium matched more with magnesium. And so what goes here? And Mendeleev was the first person, or one of the first people to sit down and say, okay, so there's an element that's there. We haven't discovered it yet. And not only have we not discovered it yet, and this is where he gets the credit, its mass is going to be 44. It's going to be a shiny gray metal, and it's going to have a melting point around 30 degrees Celsius. And he just laid that out there and was like, okay, bye. And later, I think it might have been after he died, we discovered that element, and he was right. Within 5%. It was amazing. And that's where we got that credit, that idea of maybe we should be organizing these a certain way, but we can also even say things about elements that we don't really know things about based on things that we do already know. And that brings us to the periodic table. Some things in general structure. This is the one found in your reference table. You should start to get familiar with it. The periods go horizontally and are numbered just starting with 1 and going up. So this is period 1 with just hydrogen and helium, period 2, 3, 4, and it goes up to 7. And then the groups are also numbered sequentially, but they're vertical. And that, 1, 2, 3, 4, 5. So hydrogen would be an element found in period 1, group 1. Aluminum would be found in period 3, group 13. And then that one element that Mendeleev predicted, he predicted a couple, but one of the ones he predicted was gallium, found in period 4, group 13. And there's certain reasons why these elements are placed where they are, which we're not going to get into today. Something I do want to talk a bit about the periodic table, though, is everyone always asks about this. What is this little block doing on the bottom? Why is it here? What's with the line drawing to it? How does that work? And these two rows are called the lanthanide series and the actinide series. They're also called rare earth metals. And the reason why they're put on their own is kind of because we had a structure of a periodic table, and then we kept discovering elements, and similar to Mendeleev, we found that there's this group that don't really fit with anything else. And instead of splitting the table open, we decided to put an appendix, an addendum on the bottom. If you were to split the table open, this would be the way you would organize your elements, and these are those lanthanide and actinide elements right here. They're just kind of inserted into that periodic table, and in a way, it kind of makes sense where you have these first two, and then it opens up for 2 more rows, and then it opens up for 2 more rows, and you can kind of see this pattern emerge. And that's really where Mendeleev and then we as chemists, that's where we do a lot of our work. A lot of chemistry is about patterns, how well things fit patterns, and how well things don't fit patterns. And that's what we do. In looking at this periodic table, I like looking at this one because I want to transition to looking at things a little bit differently. You can see a lot of these elements are shaded with similar colors. In doing so, I'm highlighting the big difference between the elements on the periodic table. The ones shaded over here, which I have absolutely no idea what color they are, you can let me know, not super important, but everything that's in this color is called a metal. Just like this group down here, the rare earth metals, this group over here is called the transition metals. These are the alkaline earth metals, the alkali metals. They're all metals. And so they all have certain similar properties, but also there are properties that vary among them, and there are continua that we're going to mention. And then over here we have nonmetals. And they're pretty much the polar opposite of everything that describes how a metal exists and behaves. And then there's these ones in these dark boxes, but I'm going to reference them in a few slides. So to bring that back to the table that you're going to be more familiar with, as we're using the one in the reference tables, the metals are going to be here, and the non-metals are going to be here, and the line that's between them is kind of the staircase right here. That's going to divide them. You'll notice that the staircase kind of stops right here, and we have a lot of these elements with 3 letters. The 3-letter elements are ones that are highly radioactive, do not occur naturally, and are synthesized in laboratories, and so they are given these procedural names. UUT, UUQ, they're just literally the number translated into Latin. It's like unum tritium or something like that, or unum quatrium, unum octium. And once those elements do get synthesized and the work is verified, then the labs that verify them get to name the element. Usually they're named after people or places or things like that. Or maybe like a machinery. So like these last couple here, we have Meitnerium, Darmstadtium, Röntgenium, Copernium or Copernicium or something like that, Copernicus, and then there are named after labs and locations. Your reference tables from 2011, it's a little outdated. Up to 118 now have official names. I believe 118 is Oganesum, which is named for a location where these elements are synthesized. So talking a bit about metals and nonmetals and the things between, you have a bunch of information here. I'm not 100% sure which metals are in this top picture, but they are usually this silvery gray color. They're solids, with the exception of mercury, which at room temperature, standard temperature, doesn't matter. It is a liquid. It is highly poisonous. Do not do what is in this picture. Some of the metals are less silvery gray, like gold and copper, and I think cerium or cesium. Those are a little bit, they have a bit of gold color to them. Iron is silvery gray, a dull gray. If you're thinking of red, that is a compound of iron. They are malleable, which means they can be bent without breaking. They're ductile, which means they can be stretched into like thin wires or pipes without breaking, and lustrous, meaning shiny, and then they conduct electricity and heat. All of these properties, again, are variable to a degree. They're all continua. Gold is the most malleable out of any element. I know that I think nickel as an element has a very, very low ductility, which is a good quality in maybe like a coin, because you don't want your coin being stretched and bent. You want it to keep its shape as much as possible and be durable. Nonmetals, by comparison, are everything that metals aren't. They're not malleable, they're not ductile, they're brittle. They will break when you try and bend them. They're dull, they're not necessarily shiny. They insulate, they do not conduct electricity and heat. Most of them are gases. Very few are solids. This is sulfur, this is bromine, this is iodine, this is chlorine, and this one's nitrogen. I included liquid nitrogen just to show that most of the gases are colorless, not all of them, like chlorine. Bromine is the one liquid. So there are 2 liquids on the periodic table, a liquid metal and a liquid nonmetal. And like I said, they're basically the opposite of metals in every way in terms of their properties. Now, in between, mentioned that staircase, we have these elements that we term metalloids. Usually they're kind of shiny. Usually they're kind of brittle. And then all the other properties are just vaguely in between metals and nonmetals. And that kind of makes sense because they're on the line, on this barrier between metals and nonmetals. The 6 that you need to know for the regions are boron, silicon, germanium, arsenic, antimony, and tellurium. I went and did some research. Many resources also list polonium and maybe astatine as metalloids, but I'm going to mention that depending on the sources you're looking at. But in terms of the reagents, it's those big six. And then the one thing I'm going to make a big point of mentioning is that aluminum is related to them in region, in location. Aluminum is a metal. No question about that. We consider that one a metal. But each of these metalloids is just kind of in the middle. If you were to say that malleability is one extreme of a property where like brittleness is the other, the metalloids would be somewhere in the middle. So what's nice about this periodic table is that you get this structure where these elements kind of have repeating properties. You'll start with lithium and go across to beryllium, boron, to neon, and then the next element would be sodium, and sodium actually ends up having properties that harken back to lithium. And then it kind of repeats. It's almost like periodic, which is where it gets its name. And then finally, I just wanted to mention something that the reference table gets into, and you can use this to start to discover things about elements that you might not know very much about yet, is table S. And we've already mentioned table S in terms of using the density and looking at the atomic number and the symbol and the name. And we're also going to start to use the melting and the boiling point. If you ever forget that bromine and mercury are the two STP, standard temperature and pressure, liquids on the periodic table of the elements, you can actually figure it out with your reference table, which you always have access to. First off, if STP is mentioned, that's standard temperature and pressure, and then the pressure and the temperature of standard temperature and pressure are listed on table A. We use 0 degrees Celsius. It's a little cold, but 0 is a good place to start. We also use Kelvin. We'll talk more about that in future units, but to convert between them is very easy. Just take the Celsius temperature, add 273, and you get Kelvin. The melting and boiling points on table S are always listed in Kelvin, so you might have to do some conversion to get them back to numbers that make sense to you. We don't use Fahrenheit here. But in general, if you wanted to figure out if what the phase of a given element was, and it's on table S, if your temperature is less than both the melting point and the boiling point, your substance is a solid. If your temperature is greater than the melting point but less than the boiling point, you are a liquid. And if your temperature is currently greater than both the melting and the boiling points, your substance is a gas. Thanks for watching.